All right, so today in the lecture, we're going to focus on 4 key hydraulic properties. So that'll be porosity, effective porosity, permeability, and hydraulic conductivity. And understanding the difference between these is really critical to kind of your foundation in hydrogeology. So let's get started. So our first hydraulic property is porosity, and it's often indicated by this letter N as a variable. And porosity is just the ratio of the volume occupied by voids to the total volume of the sediment or the rock. So if we were able to measure a cube, right, as we might have on the bottom left-hand side, that is the total volume, that cube. But all the space in between each of those kinds of grains that you see there, that space in between is those voids. So it's the space in the volume of that space taken up between them compared to that total volume. So you'll see in the bottom right-hand corner that we have a table that gives you an idea of the variability and porosity of these different types of rocks. And this is something you kind of always want to keep in the back of your head. I'm never going to ask you necessarily to label each one of these, but it is good to think to yourself, well, I can see that clay tends to have a pretty high potential for porosity, right? Maybe in comparison to something that might be more like gravel, which is, constrained more to the 20 to 36%. Now, you'll oftentimes see other symbols that are being used. So sometimes you'll see either this theta symbol or this epsilon symbol that is also being used to denote porosity. So it's good to kind of, when you're taking your equation sheet out and writing this one down, indicating that epsilon or theta might be substituted for N is also quite helpful. Now, the next one that we want to talk about is kind of a variation on the idea of porosity. And it's what we call effective porosity. Again, it's indicated by an N, but has a subscript with an E typically. Now, this effective porosity is actually the ratio of the volume of voids connected. And so this word connected is really key in what we're talking about here. It's the connected voids, compare the volume of those connected voids compared to the total volume of the sediment of the rock. So over here, we would have our porosity, and you can see all of those pore spaces. But inevitably, the pores that are connected and can move water here is our effective porosity. And we can see that the structure of that is smaller in many instances in comparison to what we see with the total porosity itself. Now, when we think about effective porosity, the reason, again, that we're talking about its importance here is that it's what is connected to be moving the solutes and the contaminants that we may be concerned about when we're thinking in hydrogeology in terms of the types of things that we might need to be solving for or helping with. Now, when we think about total porosity, it's usually in order of, or the total porosity is usually an order of magnitude bigger than the effective porosity. So if we look at something like anhydrite, which is the first material that we have, we see that its ranges for total porosity is 0.5 to 5, while its effective porosity is closer to 0.05 or 0.05. So it's always good to have an understanding. If you walk into an environment and you're asked, like, make a back of an envelope calculation, let's try to get down and think about what's taking place. And you've only been given the total porosity, but you need that effective porosity. First, divide that total porosity by 10 and then go ahead and get started. So the next two properties that we're going to talk about have to do with the ability to move a fluid. So permeability is indicated by this lower K, and we have to be careful. A lot of folks oftentimes get this confused. They'll start saying, well, all of these different Ks. So permeability is this lower K. And what it represents is the relative ease in which a fluid, and now this is any fluid, this is in particular, right? So this could be a gas, this could be honey, it could be anything in terms of a fluid, is able to move through sediment or rock. So some of the factors that are key about permeability is that permeability is an intrinsic property of the porous media. So porous media just means the sediment or the rock. It's important for us to put a unit with this. So you could put little k permeability on your equation sheet. And what you want to do is you're going to want to say that it's either in units of length squared. So that would be like meters squared or centimeters squared or inches squared. Or we can also talk about it in units of a Darcy. Now, 1 Darcy is equal to 9.87 times 10 to the negative 9th centimeters squared. So you can also add that to your equation sheet. The permeability tends to increase with the pore size squared. So if you have a pore size, let's say of 0.1 nanometers, and you square that, then that's going to be the relative permeability of your system. But this relationship is not as simple because pore geometries are really, really complicated. So while we can make this kind of overarching assumption sometimes to get us started in thinking about it, we have to remember that it's probably, it's very basic and has a lot of also flaws that go along with it. Our next property that we're going to think about is called hydraulic conductivity. So here's that other K we were talking about. This is the capital K, a big K. And it is the relative ease to which water is able to flow through sediment or rock. So inevitably, what we're doing is we're actually taking into consideration this idea that water itself, that fluid, has properties. And we can already account for what those fluid properties are. And so therefore we can just come up with this hydraulic conductivity, the ease at which water moves through sediment or rock. It's important for us to, when we think about this idea of hydraulic conductivity, that is a property of both the porous media as well as the water itself. And it's measured in terms of length per time. So again, I'd write this down next to the equation that you're about to write on your equation sheet. Now this looks like a velocity term, and we might want to put a little star next to this, that it isn't velocity, right? It's not the true velocity at which water is moving through the subsurface, but it is the ability for that material to move water, right? So the capacity for it to move that water. So hydraulic conductivity is equal to our permeability. And remember, the permeability is just the ability of any fluid to move through porous media, times and divided by properties of the water itself, right? So we have the density of the water that would be coming into here. We have gravity due to acceleration, and then divided by the dynamic viscosity of the water itself. So these are factors that we want to be able to take into consideration. So if I give you the hydraulic conductivity and you have these known constants that we're working with, then you can go ahead and solve for the permeability. And vice versa. So one of the key factors in thinking about this idea of being able to convert between this hydraulic conductivity with a capital K and permeability with a lower k is that understanding viscosity. And viscosity is a measure of the friction between molecules in a liquid. So we can think of high viscous materials as being molasses and low viscous materials as being things like water, or very low viscous materials being things like air. And that all of these, of course, are going to be influenced by the temperature. So you can think about the idea that if you took a jar of like maple syrup out of your refrigerator and try to pour it on your pancakes, it pours out very slowly. Also makes your pancakes cold. But if you take that jar of maple syrup and you heat it up a little bit in some warm water, and then you are able to pour it on your pancakes, you get this nice kind of smooth covering because it can pour and flow more easily, and your pancakes also don't get cold. Now, below is a table, and I'm never going to ask you, can you necessarily be able to remember these numbers. I'm not asking you to remember them, but I might ask with a table like is below to be able to actually solve between the hydraulic conductivity and the permeability. And so you'd have to look up in this table the viscosity, and you'll have to understand that all of these viscosity units are going to be times 10 to the negative third Pascal. So it's important for you to think about that. So the table below is just denoting the values that you see, and it should say U times 10 to the negative third here. So let's go ahead and write that down. 10 times 10 to the negative third over here as the units that we're dealing with in terms of our viscosity itself. So you'll go ahead and take a look and say, okay, well, at 15 degrees, this would be the value that I'm dealing with in terms of my units of viscosity. So hydraulic conductivity is actually one of the absolute most important properties of aquifers. But interestingly, right, it is one of the more extremely variable properties as well. And we have some values that we can kind of pull out as a out of our back pocket to say, well, generally these types of either rocks or unconsolidated deposits may have values that range from X to X. But what you're going to notice about that range from X to X is that it's over several orders of magnitude. So if we look at something like karst limestone, we are going from somewhere around, if we look at meters per second, 10 to the negative 2 meters per second to about 10 to the negative 6 meters per second. If we look at something like our glacial till, we have an even larger one. So here we have our hydraulic conductivity in units of meters per second, but it could be in units of Darcy, it could be in units of sorry, here are their permeability. So it's Darcy or a centimeter squared, or hydraulic conductivity, centimeters per second, meters per second, or gallons per day. So here, if we look at that glacial till and we go over to the meters per second, we see that it goes anywhere from 10 to the minus 6 all the way to 10 to the minus 12, right? That's 6 orders of magnitude of potential variability that you may encounter. And so as we move on in this class, we're going to talk about how do you deal with some of that variability in these actual values themselves. So again, here, this is just a table that gives you the ability to do some conversions between different kinds of units here. And so I just wanted to give you this table, and so you can refer back to it so that you can start to think about the idea, okay, how can we move from units of permeability in terms of centimeters squared or feet squared or Darcy's, and hydraulic conductivity units, whether that be meters per second, feet per second, or gallon feet per day. So one of the things that's going to be key as a hydrogeologist is just being able to convert between units so that you know you're able to provide and calculate things depending on what you're actually provided. And again, this is another table just to give you help. You can take a screenshot of it. We can also upload it online so that you just have an ability to be able to think about how do you convert between these different types of units, for example, an inch to a meter, or a Darcy unit to a feet per day unit.